Can we find the value of factorial half? Let's try. We know that factorial 1 is simply equal to 1. Factorial 2 is simply equal to 1 times 2, which is equal to 2. Factorial 3 is simply equal to 1 times 2 times 3, which is equal to 6. Similarly, factorial 4 equal to 1 times 2 times 3 times 4, and that's equal to 24. Further, we have a convention that factorial 0 equal to 1. That makes our work easier. But how about factorial half? Mathematician has somehow defined factorial half, and it turns out to be root pi by 2. We'll see it soon. We'll be assuming a number of results like integration by parts, and then further that we are aware that gamma half equal to root pi. We'll be assuming that we know that gamma half equal to root pi, and further we know that integral by part, which says that integral of product of two function equal to first function times second minus first function times integral of second minus integral of derivative of first time integral of second. That has to be integrated once again. So let's evaluate integral of x times e to the power minus x dx. First function, that's x, times integral of e to the power minus x, which is e to the power minus x by minus 1, minus integral of derivative of x with respect to x is just 1, and integral of e to the power minus x is e to the power minus x by minus 1, and that has to be integrated once again. Well, that's equal to minus x times e to the power minus x. Minus of minus is plus, but again we got to be integrate e to the power minus x, so minus e to the power minus x plus some constant of integration. So far so good. Now we want to evaluate integral of 0 to infinity x times e to the power minus x dx. Can we do it? Of course. Integral 0 to infinity x times e to the power minus x. If I write x equal to 0, this turns out to be 0. Upper limit is 0. If I write x equal to infinity, or if I take x limit to be infinity, then x by e to the power x, that will turn out to be again 0. And what about the other expression? So x e to the power minus x, it will always turn out to be 0, whether I write x equal to 0 or if I take x to be infinity. What about e to the power minus x, minus of e to the power minus x? If I take x to infinity, or if I increase the value of x, then we find that it is 0. So minus of 0, minus of, when I write x equal to 0, e to the power 0 is 1. So it turns out to be plus 1. So far so good. Okay, now as we said earlier, somehow we want to get the factorials or the notion of factorials. Let us apply integration by part to evaluate integral of x to the power p minus 1 times e to the power minus x dx. So we got integral by part, first times integral of second. First is x to the power p minus 1 times integral of second. Integral of e to the power minus x is e to the power minus x by minus 1, minus integral of derivative of first function. Derivative of x to the power p minus 1 is p minus 1 x to the power p minus 2 times integral of e to the power minus x is e to the power minus x by minus 1. So far so good. We could have taken p greater than 0, but we choose p greater than 1 just for our convenience. And so integral 0 to infinity x to the power p minus 1 e to the power minus x dx equal to, once again when we choose p greater than 1, the upper limit, it will turn out to be 0, and lower limit also 0, minus, minus of minus is plus, integral of p minus 1 times x to the power p minus 2. Our limit is changing from 0 to infinity. So we can write integral 0 to infinity x to the power p minus 1 e to the power minus x dx equal to, we can take p minus 1 out, that's just a constant, 0 to infinity x to the power p minus 2 times e to the power minus x dx. Okay, let's call this to be gamma p. Once again, let's take gamma p equal to, other mathematician has done it, it's just a number, x to the power p minus 1 e to the power minus x dx. Then we find that gamma p equal to p minus 1. This is just gamma p minus 1. Further, if I choose p equal to 2, if p equal to 2, gamma 2 turns out to be 0 to infinity x to the power 2 minus 1 is 1 e to the power minus x dx, which we have computed earlier to be equal to 1. And so gamma, if I took p equal to 2, we found out to be gamma 2 equal to 1. Somehow we want to associate with factorial, and we write 1 as factorial 1. Aha. Then what about gamma 3? For p equal to 3, if I write p equal to 3 here, we get gamma 3 equal to 2 times gamma 2, and gamma 2 turns out to be factorial 1. 2 times factorial 1, that's factorial 2. Again, for p equal to 4, gamma 4 turns out to be 3 times factorial 3, 3 times gamma 3, and gamma 3 is 2 factorial, so 3 times 2 factorial, that's factorial 3. Wow, gamma function is just a naturalization, or the generalization of factorials. So we find that gamma p equal to factorial p minus 1. Lastly, we want to compute gamma p equal to factorial p minus 1, yes. Lastly, we want to compute gamma 3 by 2. Gamma 3 by 2, that's equal to 3 by 2 minus 1 factorial, that's half factorial. So far so good, okay, half factorial is gamma 3 by 2. And by using the recurrence relation, gamma p equal to p minus 1 factorial p minus 1, we see that gamma 3 by 2 is equal to 3 by 2 minus 1 times gamma 3 by 2 minus 1, which is equal to half gamma half, which is equal to half gamma half, and we know that gamma half equal to root pi. We know that gamma half equal to root pi, so this is equal to root pi by 2. And somehow we were associating gamma 3 by 2 to be factorial half, so factorial half turns out to be root pi by 2.